An inclined ramp initially has no friction and makes a subtle transition to horizontal ground at its base. A small box slides from rest 2 meters down the ramp. The box transitions to the ground at a speed of 5 meters per second. What is the angle of the ramp? And then there's another question, but let's handle the first one. My recollection to you guys about this is that the only thing that Newton's laws can really tell us is the size of an individual force or the size of an acceleration. This is asking about the angle of the ramp. I'm pretty confident that the angle of the ramp is probably related to the acceleration of the box. Seems not unreasonable. If the ramp were more inclined, the box would accelerate more. That all sound reasonable to you guys? Is that a yes or a no? All right. So they give us specific information about how the object accelerates. They tell me it starts from rest, slides 2 meters, and has a final velocity of 5 meters per second. That all sounds like motion equation information. But I think there's enough information presented there that I could figure out the acceleration. If I can figure out the acceleration, I can probably figure out stuff about forces, and therefore perhaps figure out the angle of the ramp. And they tell me it slides 2 meters, starting from rest, and makes it to the bottom at 5 meters per second. There's a clear pathway to figure out the acceleration. So let's do that first, since our force problems are always about acceleration and forces and not necessarily about motion problems. So let's do the motion problem first. I'm thinking 2a delta x equals v squared minus v naught squared. So 2a times 5 equals, 2a times 2 equals 5 squared minus 0. That looks to be 25 over 4. So is that 6.25 meters per second squared? All right. Let's see if there's a way to relate the acceleration to the angle. And the answer is yes, it's mg sine theta. So I know that we can, but we'll just do the problem as if we had never done this before, but we have. So I'd say a downward force due to gravity, a normal force due to the ramp, and that'll be it. Make a coordinate system aligned with the ramp. Something like that. Break up my weight into 2 components. A component this way and a component this way. And this one is mg sine theta. Well, this one is mg cosine theta. I'm skipping some steps, but I don't feel like that's a problem. We've looked at this problem a couple times before, and I would expect at this point you guys could skip a few steps. So that seems like net force in the x direction equals ma. So mg sine theta equals m times 6.25. So cancel out the m's, and I get sine theta equals 0.625. You can use a calculator and finish that up. So what would be the size of the frictional force required to instead slide down the ramp at a constant velocity once static friction was broken? Well, we won't be able to get a value that doesn't have m in it because we don't have the mass. But if there were friction, the net force in the x direction would equal 0. So the frictional force would equal mg sine theta. So that's just going to be 6.25 times m. Question about that? All right, what would be the coefficient of kinetic friction between the box and the ramp? Well, we didn't discuss the y direction, but the net force in the y direction would also have to be equal to 0, which means the normal force is going to equal mg cosine theta. So if I want the coefficient of friction, friction equals mu times normal force. So it seems like mu is equal to friction divided by the normal force, which will be mg sine theta divided by mg cosine theta, or tangent of theta. We all good? Multiple choice. There's no real problem solving here. This would be considered multiple choice. So consider that you should be able to do a problem that is a basic inclined plane problem in about 1 to 2 minutes on the test. I'm not saying all 3 of those questions. I'm saying the individual questions there, 1 to 2 minutes. It shouldn't be a surprise that the part of the weight down the ramp is mg sine theta. That shouldn't be a surprise. So you should be able to jump right to it at this point. Well, maybe not at this point, but within the coming weeks, I would expect it. All right, so it's number 7, but let's hear that question again. A 600 kilogram plane develops a lift force, that's the force that pushes up on a plane, that is proportional to the velocity of the plane. So F lift equals some proportionality constant times the velocity. That's what that sentence says, right? The lift force is proportional to the velocity of the plane. At a speed of 180 meters per second, the plane can sustain level flight with a net force of 0. All right, so that says that at a velocity of 180 meters per second, the net force will be 0. That suggests that of the 2 forces acting on the plane at that moment, and there's probably more, I'm just really interested in the y direction forces. There will be a upward force in the y direction of lift and a downward force of weight. And they will have to be equal. Well, I know the weight is mg, which is 6,000 newtons, because it's a 600 kilogram plane. So something times 180 meters per second has to be equal to 6,000. I think I could get a proportionality constant from here. In fact, I'm going to say the proportionality constant is c, just so I have some number there, and c equals 6,000 divided by 180. Okay, what is the proportional constant of the lift force? That's what it is. The units would be newtons per meters per second. And although those would reduce to something weird, like newtons per second or something like that, just leave it like this. I'm sorry, kilograms per second or something weird, just leave it like this. What speed would be necessary for the plane to begin to ascend at a rate of 2 meters per second squared? Well, if I want to ascend at 2 meters per second squared, then I want the net force to not be 0, but to be ma. I'm thinking the plane will have to go a little bit faster. Let's find out how fast. So F lift minus 6,000 equals 600 times 2, right? The plane is accelerating at 2 meters per second squared. So that looks like F lift is 7,200 newtons. I just multiplied 600 by 2 and then added 6,000. So 6,000 divided by 180 times V equals 7,200. Am I right there? I mean, the 6,000 divided by 180, you could reduce. It doesn't have to look like that, but I'm not going to do the arithmetic. I want to see if we can get a few more of these in before I change gears. And just so you know, when I'm looking at your homework, yeah, I'm going to look at stuff like this to see what you tried to do. If all I see is a couple of arrows and you left the whole thing blank, I'm not sure I'm going to consider that to be a reasonable attempt at your homework. I want to see that you tried something. All right. A small mass is connected to a thin cord that hangs from the rear view mirror of your car. When you accelerate forward, the cord swings backward to an angle of theta. What is the acceleration of your car? What will be the angle the mass makes when the car travels at a constant velocity? When it travels at a constant velocity, the angle is going to be 0. Because there's only two forces acting on it, tension and weight, and that force has to be 0. So I'm not worried about the second question, but the first question, the system's accelerating, so I would think there'd have to be a force that pulls the weight forward and a force that keeps the object from falling to the ground. I thought we did this one in class. Okay. Yeah. So this is going to be in terms of A. Those are the forces acting on my thing, assuming that the object is in a vehicle that is accelerating this direction. So the acceleration is A. I see two forces acting on the object. I see weight, and I see tension. I think the tension is going to be greater than the weight because part of that tension has to hold the mass from falling, and part of that tension has to accelerate the mass forward. I'm going to choose a coordinate system that's aligned with the direction of the acceleration, which is this way. And that means there's a y direction that way. By alternate interior angles, this angle has to be theta. And therefore, I have two components of my tension. A component of tension that is upwards, and a component of tension that is to the right. The component of tension to the right is T sine theta, and the upwards component is T cosine theta. Well, this is a net force equals MA problem because the mass is accelerating. And it's accelerating in the x direction. Go ahead, Cami.
I'm just a little confused because isn't the ball, the ball's the mass, right?
Yep.
So isn't it not accelerating and that's why there's an
No,
angle?
it's accelerating.
The opposite way? But I thought the whole thing is like the car is accelerating, not.
It's attached to the car. Yeah. If it's not attached by the string, it won't accelerate. It'll just roll to the back of the car. Something has to pull it forward. What do you think is going to pull it forward with the car? Right? It's got to be the string that makes it go forwards. If it's part of the car, there'll be a time, a transitional time when it goes from being at 0 to being at an angle, where the motion of the car and its own inertia work against each other. But once it's accelerating at the same rate as the car, it's going to form an angle. For a time, the car accelerates and it hasn't yet started to accelerate, or at least not at the same rate as the car. Same reason the car starts by starting to lean the car backwards when you accelerate. The car has inertia, it's resisting changes in motion. But still, this will be tension sine theta equals MA. And then the y direction, I'm going to have tension cosine theta equals mg. If I just divide both sides of these equations, I'll get tangent theta equals a over g, or the acceleration equals g tan theta. So if the acceleration is 0, the angle's 0. All right. Okay, not a whole lot to work with here. So I have a small mass that's hung on the end of a string. So end of the string, small mass. Because I'm going to exaggerate it a little bit to make it easier to see this, but it's traveling in a circular path. So that's our circular path, something like that, going maybe this way and this way. Everybody follow along with what's happening? Any questions about it? All righty. Tells me the length of this is 20 centimeters, but I'm just going to use L for the time being, and I'll put the numbers in last. It says the mass is 10 grams. Again, I'm going to say the mass is M, and this makes an angle of 25 degrees, but I'm just going to call it theta. And then again, I'll put all the stuff in at the end. Well, I think there's just two forces acting on the mass. There's weight acting downwards, and there's a tension acting this way. And the tension's acting at an angle of theta as well. So since we just did a problem like this, I think I can skip ahead a little bit and say the net force in the x direction equals ma, and the net force in the y direction equals 0, except in the x direction, instead of it accelerating in a straight line, it's traveling in a circular path. So this is MAC. That's it. It's the only difference. So everything else is going to remain the same. So it seems to me T sine theta is going to equal m v squared over r. We don't have t though, so we're going to need to find a way to get t. But we know that t cosine theta equals mg, and we do have m. So I see a pathway to eliminate t, and the problem wants the velocity, so I think we're looking for v. All good so far? Any questions about what I'm doing? I would expect after our conversation yesterday, you could get to here. So if you combine problem number 1 and what we did yesterday, the only difference is that one substitution. Now maybe you were confused as to know what to do here, or maybe you didn't do that one last night because I said I'll give you a couple extra days and it's not in your purview to work ahead. I'll know when I see the homework you submitted. But that's the only substitution, except we need r. What does r represent? Radius of curvature, and the radius of curvature in this problem is this distance. But I think we can get something in terms of the length they gave us. Do you see a triangle there that would help us figure out r if we have the length? Because I see a triangle there. Something probably like r equals L sine theta. You guys see that all right? All righty, let's start putting some stuff together here. I'm going to solve for, I guess I could solve for tension, or I could just divide both sides of the equation to eliminate m. Do you guys have a preference about how I do this? So if you have no preference, that makes it easy on me. I'm going to say T sine theta equals m v squared over L sine theta. And I'm going to divide this side by T cosine theta and this side by mg. If I do that, cancel out the t's on that side, and I'll just get tan theta. And cancel out the m's on that side, and I'll get v squared over LG sine theta. I just need v by itself, so I think that's some pretty short algebra. Multiply both sides by LG sine theta. And take the root. Think we're done? I mean, there's another question, and I'll answer that one if you'd like, but I think this is the heavy lifting part, right? I don't think many people attempted it. You can usually tell there'd be questions. So I want to know if I'm even close, and you guys would say, I have no idea what I'm doing. There's a way to check. My answer is the square root of LG sine theta tangent theta. Tangent theta has no units. Sine theta has no units. But what are the units of G? What's that? Meters per second squared. What's the units of L? If we don't want to participate, it's okay. I don't have to go over homework. Probably meters, if I want to be in consistent units here. So if you're going to use G, which is going to be in meters per second squared, you'll have to convert that length to meters. And this is all to the 1/2 power. So this looks like inside the parentheses is meters squared per second squared, and I'm taking the square root. My answer's in meters per second. It seems pretty clear that I haven't made any algebra mistakes, because I'm getting an answer that's in the appropriate units. Now, if you want to figure out how long it takes to go around that circle, we did that yesterday too. Velocity equals 2 pi r divided by t. Solve that for t. All right. The idea is I have chair, I have person sitting in chair, and there's a rope that goes over a pulley, and then that rope comes back to my hands, like so. And together, all of this has a mass of 65 kilograms. You pull on the rope so that you in the chair are suspended from the ceiling. What is the tension in the rope? All right. Let's look at the forces that act on the chair-person thing. I know the chair-person thing has a combined weight of 650 newtons, right? Seems to me that there are two tensions acting upwards on the chair. There's the tension from the part of the rope that's in my hand, and the tension from the part of the rope that's attached to the back of the chair. They'd have to be equal, because if one was greater than the other, then that would mean that the string is separating or breaking, or one part's accelerating more than the other. And I don't think that that's what's happening here. It said the whole system's at rest, so those would both be the same. Tension and tension. So what is the tension in the string? Well, net force equals 0 if I'm at rest, so 2t minus 650 equals 0, t equals 325 newtons. The idea of a window washer's rig is you don't have to lift your own weight, just half of it. That's the way it's designed, so you could get up to the top of a building and wash the windows. If you pull on the rope with 400 newtons of force, what will your acceleration be? Will it be up or down? Well, it's going to be up, because I've increased the tension beyond the 325 newtons. And let's see, we can do that one. If I pull on the rope and add tension, I wouldn't be able to do that very long, I don't think, I'll be honest, because that's accelerating. So we're probably only accelerating to get us started, and then we'll probably start using a constant velocity and go back to 325. But for a moment, the net force will equal MA, and it will be 2 times 400 minus 625 equals, not 625, 650. 650 equals 65 times A, and that will be the acceleration. That's 800 minus 650, which is 150. So the acceleration is 150 over 65, whatever that is, I don't care. If you want to do the next question, I'm not going to do it. Just put in 0.5 for A and solve for T. Oh, wait, 0.5 downwards. So put in negative 0.5 for A and then solve for T. In a banked roadway like this, and the problem is, is talking about the road being iced over. But we have in Florida quite a few of these freeway knots where there's quite a few banked ramps. And the banked ramp is there to allow you to pass through the roadway at the same rate of speed that's reasonable, but not rely 100% on friction or any friction. So the proving grounds that most of your automobile manufacturers used to use to test vehicles would allow stress testing of vehicles where they would drive the vehicle for a week and refuel it while moving to stress test the vehicle. They have a continuously changing bank angle, and the drivers can just set the car at a specific speed on their cruise control, and it will just come up to the appropriate banking and just stay there, not having to steer, using just the action of gravity as a means of the car traveling in their circle, doing their stress testing. The thing that you have to understand about this problem is that once you have a bank angle, the normal force is no longer the same as the weight. It is the normal force that is helping push the car in the circle. So the weight of the car is less than the normal force, as the normal force is helping the car bank. So what you need to do here is not follow the tradition you've been following before and making the ramp the direction of the acceleration. The car is not accelerating this way. The car stays on the ramp. The car is accelerating through the turn. You need to make the X direction this way. So that this is the positive X direction. That's towards the center of the turn. So I'll remind you that for an object travel in a circular path, there must be a component of the unbalanced force towards the center of the circle. Down the ramp isn't towards the center of the circle. So you'll break the normal force up into a component upwards in the Y direction, and that one is equal to 0. And then the other component of the normal force in the X direction, that one is equal to MAC. But okay. I would encourage you to look at questions like 19, because it's adding other things into the problem that you might have to deal with, like an angular speed at 33 RPM. But I would also call your attention to question 20. Question 20 is the first real question where we're no longer dealing with just stuff that would be in AP Physics 1. It's the first time that you'll have to deal with calculus. In that problem, it's talking about a skydiver jumping out of an airplane and the fact that the skydiver is experiencing two forces. One of the forces, that's obvious, is weight. The other force, however, is drag. But the drag is a force that is proportional to the velocity. There's a negative sign in the expression. That's because the force is in the opposite direction of the velocity. But since we assume the guy's falling downwards, I'm going to leave out the negative sign for this picture. Now, it should be clear that when the guy first jumps out of the plane, his velocity is 0. So there's no drag at time equals 0. And then as they fall for a while, they will eventually reach a steady state condition where they will be falling fast enough for the upward force to balance the downward force. This is called terminal velocity. You should look at this question tonight. So fishing line. I assume we're going to pull this way on the fish to get them into the boat. And I don't want the line to snap. The max tension can't exceed, or has to be, we'll say has to be less than 25 newtons. And there we go. I think net force equals MA in this problem, and that there are two forces acting on the fish. There's going to be the upward force due to tension, and there'll be the downward force due to weight. And these are unequal, as I assume we are accelerating the fish upwards towards the boat. So mg and tension. Good so far? Tension minus mg equals ma. So tension equals mg plus ma. Mg plus ma must be less than 25 newtons. That enough? Okay. Multiple choice. I think that's a reasonable multiple choice question. Bless you. In this question, it's tough if you don't understand a portion of the problem. So this is about a banked turn. This is not like the turn we talked about yesterday. In a banked turn, the roadway isn't flat. So let's consider that in a banked turn, and I'll do my best to facilitate a car, but we understand that that's not going to look much like a car. We thoroughly made that clear to Mr. Shelton yesterday. And it's worse today. So there's our car. We'll say that the car is traveling in a velocity that is into the page. And we're looking at the back of the car. The velocity of the car is this way. That all right? Now, if we're behind the car, so we're here in this picture, we are, say, here. Can I assume all of you realize the car, the banking of the road would be this way? Does that make reasonable sense? Banking it the other way would be dangerous, right? Especially if the roads were icy, because this would want to, we already know the car wants to go in a straight line, which would be a straight line in the direction of the arrow. You make your road bank this way, even without moving, you might just slide right off the road. So the better direction for us is going to be that way. Now, here's where you may not understand how this works. The car has a weight that is clearly directed downwards. We've been talking about that for a while. And there's a normal force here too But what I don't know you understand is there has to be a force directed towards the center of the circle. And with that in mind, the force towards the center of the circle has to come from somewhere, and it can't come from friction. So it is the normal force that actually pushes the car through the turn. So your normal force is actually going to be greater than the weight, because a portion of the normal force is pushing the car through the turn. And if you don't understand why this is, if you've ever watched, ever played with Hot Wheel cars and such, the track's moving all over the place when the car is passing through it. It's because the car has inertia and the track is trying to apply a force to the car, and it bends when it does so. We don't want our roadway to bend, so if I want my car to make this turn, I will need a force, or at least a component of a force, that is towards the center, this way. I know with the other ramp questions, we've made our coordinate system down the ramp, but do we want the automobile to accelerate this way? I mean, we don't. We don't want it to slide down the ramp. We would like an acceleration towards the center with no component up or down. A component upwards would mean just as much of a problem as a component downwards, because a component upwards would mean we'd be going up to the outside edge of the ramp. So I'm going to set a coordinate system that is based on the horizontal and vertical of the problem. So my coordinate system will be this way. And I'll make also a complementary direction this way. And this yellow arrow represents the component of the normal force towards the inside of the track. And there'll be another component of the normal force that is upwards. It is the component that is upwards that is balancing the weight and keeping the car level on the embankment. So this will be normal cosine the embankment angle of theta, and the top one will be normal sine the embankment angle. And of course this will be mg. So net force in the x direction will be MAC, and net force in the y direction will be 0. It tells me the road is banked 25 degrees. I'm getting normal cosine theta equals mg, and normal sine theta equals mv squared over r. Now, as r was not given in the problem, our answer is going to have r in it. But I think you probably can negotiate this. Are you guys in a position where you think you're okay to solve for v in terms of the other variables?
Yes, sir.
So I would, for those of you who aren't, I would just take and divide these two equations. The normal force will cancel out, and so will the mass of the car. This embankment angle is good for any size vehicle, which is good. But without r, you're not going to be able to get a numerical answer. By the way, if there is friction, there's actually two possible answers then, or two possible ways to conceive of it, but one answer that is right. If there's friction and they want the maximum possible velocity of the car, that means there's going to be a frictional force you have to add to this problem, and the frictional force would be this way. The frictional force would add a component to your capacity to drive around this curve. So you would go faster. There'd be a portion of the friction towards the center. That's a challenging question for anybody who's just starting out. So I would say that if you're barely grasping this, I wouldn't worry about that question. But if you're doing pretty well, you should give it a shot. Here, I'll make it easy. Let's say at the embankment, the banked curve has a radius of curvature of 100 meters. That way you don't have to worry about your R anymore. Again, if you want to try this one out, let's say it has a 100-meter radius. All right. So in a problem like this, it's still a net force problem. And in the first instance of the problem, the person is just suspended. So there's no acceleration. I would suspect then that there will be two forces acting on the person. Weight downwards and two tensions upwards. One from the one the person's holding and one that's attached to the chair. And although the downward force is weight, the tensions would have to be equal. If they weren't and the tensions were unequal, that would mean that the rope is stretching or shrinking or something, right? Because one part would be accelerating compared to the other. So in a rope or a string, the tension will be uniform everywhere in the rope or string. At least that's how we will treat ropes and strings in this class. I would consider writing that down. No matter what the problem is, if your pulley has no inertia, that's a big if. If your pulley has no inertia, then the tension in a string or rope will be uniform. All right. So at the start of this problem, it's a net force equals 0 problem. So 2t minus 650, because the person's mass and the chair is 65 times 10, 650, equals 0. So the tension is just going to be 325. But then it goes on to say that you apply a force of 400 newtons to the rope, which means the tension pulls up on you with 400 newtons. That also means that the other side attached to the chair is also pulling up with 400 newtons. So I think the chair is going to accelerate upwards because the two tensions have suddenly increased. Now, the whole point of the windows washer's rig is that you don't have to lift your entire weight. So if you can't climb a rope unaided, this is a way that you could use the idea of climbing a rope to cut the force in half. So you guys who go to the gym and stuff, what do you think all those pulleys are doing? They're there to leverage the weights that you're lifting, but they're also there to make sure it's within your capabilities. So I know most of you probably can't climb a rope. Since they don't even test it in schools anymore, you don't even know if you can, most likely. But you should try, or consider trying it. There's no reason not to. You're all young and spry. But we'll get 2 times 400 minus 650 equals 65A, since this is now a net force equals MA problem. This will tell you what the acceleration of the person is upwards. Now, the last one says that what tension would you have to keep in the rope to accelerate downwards? Now, trust me when I say, I don't think you're maintaining 400 newtons of tension in the rope. I think you put a little extra tension in the rope to get yourself started, and then you probably go back to applying only 325 newtons of tension in the rope as you climb upwards, right? There's no reason to accelerate to the top of the roof. You got a long day's work ahead of you if you're washing all those windows. But if the acceleration is downwards at 0.5, we can just reuse all this stuff and say 2t minus 650 equals m times, well, we know m is 65, so 65 times negative 0.5 meters per second squared. We don't have to make the direction of the acceleration positive. So if we're accelerating downwards, we just make it negative. And this will tell you what the tension is. I bet you're going to get a value that is less than 325. All right. How hard it is. And I'm going to point out that your cries will go absolutely nowhere. Is it going to be a massive surprise that when I say the lift force on a plane is upwards on a plane? The lift force lifts the plane. It's called the Bernoulli force, and it comes from the Bernoulli principle, that air passing along the top of the wing creates an area of low pressure, and the air passing over the bottom of the wing is at a higher pressure, and it pushes upwards on the wing. It has to do with the flow of air across the airfoil. So with that said, I thought the word lift was probably sufficient. In this problem, it says the plane is traveling in level flight. So that suggests that the net force is 0, with mg downwards and the force of lift upwards. There's probably a horizontal force on the plane too, propulsion of the engines, called thrust. And there's probably air resistance too. But I don't have to worry about any of those. We're said that the plane's in level flight. I'm worried about the up and down force on the plane. And they said the lift force is proportional to the velocity. I put a blank there because the moment I put a letter there, you're going to say, where did the B come from, or where did the X come from? I just need a letter. So right now I put a blank there. So that's a proportionality constant, correct? That's what a direct proportion looks like. So I just read the sentence and wrote a mathematical version of the sentence like you would do back in the 3rd grade. But I'm probably going to say F lift equals proportionality constant times V, because I just want a placeholder there. This is algebra, and we've learned that we can use any letter we want for a placeholder, right?
Yes.
Well, we'll see, because earlier today that was not particularly acceptable. It says the plane is in level flight when it's at a speed of 180 meters per second. Alrighty, so CV minus mg equals 0 when V equals 180. So C must be equal to 6,000 divided by 180. I cut some steps out of there. Speak now if you need me to put those steps in. So it says at a velocity of 180 meters per second, a 600 kilogram plane acted on by gravity at 10 meters per second squared would have a net force of 0. So if I wanted to solve for the proportionality constant, I'd get 6,000 divided by 180. You can kill a 0 if you want, and kill a 6 if you want to, and get, what, 100 over 3? So that's newtons per meter per second. And yes, you could break that down, but there's no reason to. This makes the sense of the problem, that our constant is in terms of newtons and speed. So I'm going to leave it like that. What speed would be necessary for the plane to begin to ascend at a rate of 2 meters per second squared? Pretty sure the plane would have to go faster, right? If the lift force is proportional to the velocity, and I want to make the velocity a bigger number, so this will be the case where net force equals ma, which will be CV minus mg equals ma, or 100 over 3 times v, minus 6,000 equals 600 times 2. All right, the acceleration is upwards of 2 meters per second squared. So 100 times divided by 3 times v equals 7,200. And I think we've done enough work here. Alrighty. Not a tough one. Multiple choice. Yeah.
For number 13, I don't need you to solve.
Well, I don't know what the bug's trying to do.
When you spin it, you mentioned how it's trying not to fall off the edge of the disc, and then, so I would assume that you want it to move toward the center. But then you use this formula, which was m.
A bug crawls on top of the record. You decide to turn on the record player, and when the record player is spinning at 33 1/3 RPM, the bug is able to stay 12 centimeters from the center of the disc and not fall off. What is the minimum coefficient of static friction that must exist between the bug and the record? All right. Is this the problem we're discussing?
Yes.
All right. I'm not going to put any numbers here, just going to work the problem out, and you can plug in numbers on your own time. I'm going to use an angular speed of omega is how fast the record player is going. They gave it to us as 33 1/3 RPM. I'm just going to leave it like this, but you can't use RPM. If you want to use RPM, you're going to have to convert it to something else. For the way I'm going to do the problem, I'm going to leave it in terms of omega so I can show you something. And so I'd pay attention. This is not just me going over a homework question. This is me adding to the things you're supposed to know. Does everybody understand what I'm saying? In fact, in this problem, you would have to convert RPM to radians per second to do what I'm about to talk to you about. Because something I said yesterday is that the bug's linear velocity at this instant, based on an angular speed of omega, is v. Well, I'll put a t next to it so we know that we're talking about the tangential speed of the bug. You're going to start seeing me do this because we will have problems where the bug might start walking towards the center of the disk, where they will have two velocities, a radial velocity and a tangential velocity, right? So if the bug decides to start walking this way, understand that that would be two different velocities, one initiated by the bug, one because the bug is on a moving platform. You all following? So T represents tangential. It's tangent to the circle. And what I said yesterday is that equals omega times r, where r represents the distance from the center to where the bug is, the radius of curvature. But you can only use that formula if you are in radians per second. So you would have to convert your RPM to radians per second. Nobody blinked an eye at that yesterday, so I can assume you guys are proficient at converting. If that's not true, you had probably better let me know someday, because I'll just assume you guys are excellent at it. But you guys hate to be seen as not knowing something. Trust me, get over that. If centripetal acceleration is vt squared over r, and if vt is omega times r, you might be able to do this problem in terms of the angular speed and not ever convert to a linear speed. Do you see the algebra I've just done? I would certainly like you guys to have that information at the ready, because there's no reason not to know this. It will make this easier on you. So, the bug is experiencing, I think, three forces. I believe the bug is experiencing weight, normal force, and friction. And that frictional force would have to be towards the center. That's static friction, that's normal, and that's weight. All good? It is the frictional force that is causing the bug to travel in the circular path. So I would say that net force in the x direction equals MAC. So friction is equal to m omega squared times r. Any questions? Are we sure? Who's got a question? Then Elijah, you should say, Mr. Sheldon, you can't see me because you got your back to me, but could you answer my question? I wasn't. If I don't see a question, I can plod on and just, go right past
So
you.
in the top left with the AC equals VT
I know
squared.
it's written there.
Yeah, so over there, you said that's like something we should put down. Could you just explain what exactly it is?
It's just another way of writing the centripetal acceleration. So now, if you know something's traveling in a circle, you can write the centripetal acceleration in terms of its linear velocity, that's the first term, or if it's on a spinning platform, you could write it in terms of its angular velocity, that's the last one. So the kids on the carousel horses yesterday. It's fine. And it also tells you something. Because yesterday we weren't real sure what the relationship was between like the force required to travel in a circle and your radius away from the center. It's clear, it's linear. If I double how far away I am from the center, it takes twice as much acceleration to be there, which means twice as much force. Right? It's a linear proposition there. So I think it's good to have that. All right, that good?
Yeah.
All right, at the same time, net force in the y direction is 0, so normal equals mg. All right, that's all Newton's laws can do. However, we know more things. We know that static friction is less than or equal to mu times the normal force. If I want to create an inequality that would tell me where I stand on speed or radius or whatever, I'm going to plug into this function with m omega squared r being less than or equal to mu s times mg. Does everybody see what I've done? All right, I like this because this tells me, first, doesn't matter how big the bug is. From a tarantula down to a cricket, down to a little tiny ants, same idea. Except that they have sticky stuff on their feet, so I don't know if mu will be the same for all of them. I like this because it gives me a conditional. It tells me that mu s has to be greater than something, but it also tells me that the radius will have to be smaller than something, or the angular speed will have to be smaller than something. You guys see what I'm saying? It helps me understand the direction of whether something is a minimum or something is a maximum. The left side, those are things that will have a maximum that we can't exceed. There is a maximum speed, can't exceed it. There is a maximum radius, can't exceed it. But on the right side, there are minimums. There is a minimum coefficient. If I get any lower than that, bug's going to fly away, off the record. All good? All righty. I think that really explores that problem all the way, doesn't it? Once you develop that, you can do everything else in this problem. Don't forget, this still has to be radians per second. All right. That leaves me with just a short amount of time, 2 minutes. The real problems, the fun ones, are like questions 20 or 21. These are fun problems. Problem number 20 is about a skydiver who is experiencing a force of drag which is proportional to the velocity. It's a vector equation, but the negative sign there is to indicate that if the diver jumps out of the plane, and I think it's not a huge stretch to say the diver will fall downwards, then drag will oppose the direction of the fall and we will create an upward force. So the drag force will be upwards when the weight is downwards. So this is mg, this is force of drag, which will be kV. That means net force equals ma, maybe. I say maybe because this is going to be mg minus kV. I'm making downwards positive. That makes the most sense since that's the direction the skydiver is going to accelerate initially. Once you think about this, at time 0, the velocity is 0 because they've just jumped out of the plane. Gravity hasn't had much time to work on them yet. So at time 0, there is no drag, right? They've just jumped out of the plane, they're not moving yet. However, as time increases, the velocity will also increase because they're accelerating downwards. Gravity's pulling them downwards. So for a time, the drag force will be less than the weight. But do you realize that after a while, they're going to keep accelerating downwards? Eventually, the net force will be equal to 0 because as they fall faster and faster, kV becomes bigger and bigger. When that occurs, mg equals kV. This is called terminal velocity. What's interesting This doesn't happen in a linear way. As the velocity increases, the acceleration is decreasing because the upward force is getting bigger. This is complicated. This will produce a complicated situation. An interesting one.